All right, let's get right into it. Today, we've got a real showdown for you. A battle between two absolute titans of function approximation. In one corner, you've got the classic, the elegant, the mathematical champion of old, the Fourier series. And in the other corner, the modern tech giant, the powerhouse that's shaping our world as we speak, the neural network.
But here's the thing, and it's a real head-scratcher. We have this classic mathematical tool that's been proven to be able to approximate basically any function you can think of. So why on earth did we go through all the trouble of inventing something as complicated as a neural network? That's the big mystery we're going to solve today.
So first up, let's meet our reigning champ, the Fourier series. I mean, for over 200 years, this thing has been the secret weapon for mathematicians and engineers. It's how they break down incredibly complex signals into simple, easy-to-understand parts. It's beautiful, it's proven, and it is just incredibly good at what it does.
Now, what do we even mean when we say function approximator? Well, think of it like this. Imagine you've got this super complex squiggly drawing, right? An approximator is a way to recreate that drawing, not by copying every single dot, but by using a bunch of simple, predictable shapes, like circles or waves. It's all about capturing complex stuff using simple building blocks.
And for a Fourier series, those building blocks are just good old sine and cosine waves. You know, the simplest waves there are. And just by adding these waves together, with different heights and different speeds, you can build up and perfectly match almost any signal you can imagine. It's what helps us understand the difference between a violin and a piano, and it's even part of the magic inside your noise-canceling headphone. And here's the kicker. It is so good at this. For the right kind of problem, what we call smooth functions, Fourier series have this almost magical property called spectral convergence. As Reddit user Chris Rockaukus puts it, this means your error, how far off you are from the real thing, doesn't just get smaller, it plummets exponentially. This is the gold standard of getting accurate fast. So you've got to ask, why would you ever need anything else?
And that, of course, brings us to our challenger, the beast from the world of modern AI and big data, the neural network. This is the tech behind, everything from recognizing your face in a photo to translating languages on the fly. And at its heart, it's also a function approximator.
Okay, so a neural network is also a universal approximator, but it plays the game completely differently. See, instead of fixed building blocks like sine waves, a neural network learns its own building blocks from scratch. The analogy I love is this. A Fourier series gets a box of standard-sized Lego bricks to build with. A neural network gets a lump of clay, and through training, it learns how to shape that clay into the exact custom pieces it needs to perfectly model the data. They're adaptive, not fixed.
So here we are, back at the big question. We have two different methods that can, in theory, do the exact same job. One of them is proven to be insanely fast and accurate for the right kind of problem. So why aren't we just using Fourier series for all our machine learning? Why isn't it the king of everything? There has to be a catch, right?
Oh, there is a catch, and it's a big one. It's a concept so famous it sounds like it's straight out of a sci-fi movie. The curse of dimensionality. This is the hidden weakness of our classic champion, and it's the very reason neural networks exist at all. To get this curse, just think about data. One-dimensional data, like a sound wave, is pretty simple. It's just a line. Now think about a simple black and white picture. That's 2D data, a grid of numbers. But what about a high-res color photo from your phone? Now you're talking about a massive structure with millions of numbers. Every single pixel and its color value is its own dimension that you have to worry about.
And here's where it all falls apart for Fourier. To make it work in higher dimensions, you can't just add a few new waves. No, you have to add terms for every single combination of how those dimensions interact. The number of terms you need doesn't just grow, it absolutely explodes.
Get this. Let's say you have a function with 100 dimensions, which, by the way, is tiny for modern AI. If you wanted to use a Fourier-style method just to capture the simple third-level interactions between those dimensions, you would need over 161,000 terms. It is just completely, utterly unmanageable.
And that, my friends, is the curse of dimensionality. It's the knockout punch. As your number of dimensions goes up, the math and memory needed for something like a Fourier series just skyrockets exponentially. It makes it totally impractical for the kind of data that defines our world today. Images, video, language, you name it.
So if the Fourier series gets completely flattened by this curse, how do neural networks survive it? Well, it turns out they were basically designed to handle this exact problem. It's their superpower. Okay, if you remember one thing, remember this.
The cost of using Fourier-style methods grows exponentially with more dimensions. The cost of neural networks, on the other hand, grows polynomially. Now, that might sound like a subtle difference, but it's really the difference between something being literally impossible and something being, well, possible.
So, how do they pull it off? Well, instead of trying to model every single possible interaction, a neural network is smart. It learns to focus on what's actually important in the data. It adapts itself to find the patterns and features that matter, and it basically learns to ignore the rest. It doesn't need a term for everything, just for the things that help it make the right call.
So this really isn't a story about an old champion getting knocked out by a newcomer. It's about a new tool being invented for a totally new kind of problem. It's about understanding that in this game, there's rarely a single best tool. There's only the right tool for the job you're trying to do.
And this table really says it all. If you're solving a complex physics problem or running a weather simulation, things with a relatively low number of dimensions, Fourier-based methods are still the absolute king. That spectral convergence is just unbeatable. But if you're trying to teach a computer to find all the pictures of cats on the internet, you're in a high-dimensional world, and that's where neural networks shine, because they were born to beat that curse.
And Chris Rakauskas on Reddit just sums it up perfectly. Being an expert here isn't about picking a favorite. It's about understanding the deep theory behind your tools so you can pick the right one for the right reason and get the absolute best performance.
And that leaves us with one last big question to think about. Neural networks were created to handle the curse of dimensionality, a problem that stumped the tools that came before. But as our data gets even bigger, even more complex, what's the next curse waiting for us out there? And what will the next generation of tools, the ones that solve that problem, even look like? I guess we'll just have to wait and see.